we're going to review for exam 2 on chapter 12 and use this version 2 review document. It's different than the one I handed out, but it should be available in Brightspace as well. If you can't find it in Brightspace and you need it, let me know. All right, so as usual, let's see, there we go. I'm going to work from the ones that are highlighted. So in this case, number 1, if the reaction is first order, and so our reaction is H2O2 iodine, 3 iodine, 2 hydrogens, yields 3 + 2 waters. Okay, if it's first order in this one, and it's second order in this one, and it's 0 order in this one. Okay, then we want to write the rate law. Remember, when you've got a balanced equation, an overall equation, these values don't mean anything to the rate law. When you say the rate is equal to something, in that case, we need a rate constant. Then we need a factor for first order in this one, okay? Second order in that one, and 0 order in this one. Right? If it's 0 order, it's equal to 1, right? So it's not even there. That's where most students get mixed up. They'll write this one in here and put a 0 on it. Or they'll look for the one that has that in it, and A does have that one there, but you don't put it there because anything to 0 power is 1. So that term drops out. And the one that you want is E. Okay. All right, moving on. I wonder if I can use this. Probably can't. No, it's not behaving. All right, do it the old-fashioned way. Let's see. I'm gonna have to move. You guys can't see this, but these thumbnails are in my way. Here we go. Number 2. A reaction has the rate law, A squared B and C squared. Okay. Second order in A, first order in B, and second order in C. Okay. What's the overall order of the reaction? Don't look. 2 + 1 + 2. 5. That's the overall order. Okay. It's second order in A, first order in B, and second order in C. But overall, it's order 5. Right. Let's see. I think I skipped over this one. Yeah. It's a little bit too much to chew right now. Okay, we got those two together. 4. If the reaction 2HI yields H2 and I2 and is second order, right? Can we do that? Can we say second order here? Yeah, because usually the order references the reactants. If we said it was second order and we didn't know that, then we'd have to say something about these together. Right? And that's a little more difficult. So it's second order with respect to HI. Which of the following will yield a linear plot? So if we have the rate law here, okay, and then HI is second order, how would we plot time against concentration of HI? If we plotted just these values in its second order, what would you get? You get a curve, right? If you take the natural log of this one, right, and plot time against that one, what do you get? You get another curve, right? It's not a straight line. But if you take the inverse of that value, you get a straight line with a positive slope. These are both curves with negative slopes, and this is a straight line with a positive slope. So you plot the inverse of HI against time, you get a straight line. Okay? Okay, number 5. Which of the following statements about enzymes is incorrect? Okay, so we got A, B, C, D, and E says all are correct. So that means we got to look at each one. All right, how about the first one? They're usually proteins that catalyze specific biological reactions. Now, we didn't discuss that. That would come out of your textbook. Right? But that is true. They're usually proteins and they catalyze specific reactions. I did mention that one. They work on specific reactions in one direction, usually. Most of them do. So that statement is true. They're equal to inorganic catalysts in efficiency. That's false. Inorganic catalysts are very inefficient. Enzymes are very efficient, extremely so. Right. So we know that E is not correct. And we found one that's false. Let's just for giggles, several thousand are known. At the time this question was created, that's true. But they're probably tens of thousands by now. So true, up to that point, there are several thousand known, but there are also several 10,000 known. And D, the molecules they react with are called substrates. That is also true. You have an enzyme reacting with a substrate. If you're going on to biochemistry, well, you have to go through organic first. But nobody, okay. But if you're ever introduced to biochemical reactions, the object, the reactant that or reactants that combine with the enzyme to facilitate the reaction are called substrates. So when you eat something starchy, right, you swish it around in your mouth, there's an enzyme that's immediately in your saliva. It's called amylase. And it takes starches and breaks them into simple sugars. So if you keep them in there long enough, they'll start to taste sweet. The substrate is the starch, and the enzyme is the amylase. Most enzymes end with that suffix, ase, something, ase. All right. Let's see. We're going to skip 6. I know I've got a sample problem in here for method of initial rates. That's not it, so we'll just skip that one. Number 8. Let's see if I can get them both on there. Yeah, number 8. A free radical is a chemical species that possesses what? What's a free radical? Okay, by definition, a free radical is any chemical species. It doesn't have to be atomic, it can be molecular. And just to represent the species, whatever it is, if it has at least one, and that's usually the case, one unpaired electron, that's a free radical. They're very reactive. And those are the kinds of things that they believe damage your cells. Right? Certain types of foods are more prone to produce free radicals in your body. And your body has enzyme systems that scavenge those free radicals before they can do any damage. And they think that's one of the things that happens when you age. You start to lose the ability to scavenge those free radicals, and they damage your cells, and you get aging diseases. Maybe even cancers, for that matter. What's a cancer? I'll digress for a minute. A cancer is at least one cell that's lost the ability to control itself. It will not stop dividing or will not stop growing. And the natural systems that regulate those processes are lost. So one of your cells just takes off and starts multiplying and produces a cancer. That's a general definition. There are specific definitions for all kinds of cancers. The rate expression for a particular reaction is AB squared. So we're saying the rate is equal to K, A, and then B squared. Okay. If the initial concentration of B is increased from 0.1 molar to what? 0.4 molar. The initial rate will increase by which of the following factors? Well, how much did it increase here? It went from 0.1 to 0.4. It increased 4 times. We increased the concentration by a factor of 4. So this 4x in here is squared. So it's 16 times the rate. If you do that to B, if you change the concentration by a factor of 4, you increase the rate by a factor of 16 because you square that. Okay? And that's why the answer is C. Now, if we did that over here, right, 0.1 and 0.4, and this one stayed the same, then it would only be a factor of 4 because it's to the first power. Okay? What if we did both of them? 0.1 and 0.4 for this one and 0.1 and 0.4 for this one. Okay. You'd have 16 here times 4. 64 times. Okay. We didn't have time during the lecture to theorize about these uses. That's why the review is so important, because we pick up these practical applications of the rate law. Number 10. There's 2 new things today. The crossword puzzle I forgot to give you 2 days ago. And then the document we're working from today has the yellow highlights on it. Okay. You probably got the others already.
Yeah, I got the other one.
You just need that one and the it's thick.
Okay.
That one in the crossword. And I'll remember to hand out the crosswords on the day we lecture next time. For which order reaction is the half-life of the reactant proportional to 1 over K? So the half-life, E1F, we want to see which one is proportional to 1 over K. I think I did make a point of this one. So, and your useful information, I think I've included those. Yeah, I've included the half-lives there. right? So you don't have to memorize them.
We're working on this one, right?
Yeah, the one with the highlights on it. So the half-life for the zero order is short-term memory loss. A0 over 2K. And 0 over 2K. That's zero order. First order, the half-life is 0.693 divided by K, I believe just K. Yeah. And then the second order is 1 over KA0. Good. So those are the half-life formulas for each one of these orders of a single reactant. Example, make different orders when you only have one reactant. Okay. So which one is proportional to 1 over K? They all are. They're all proportional to 1 over K. So that's why D is the answer. I thought that was neat. All right. How about who's next? 13 and that'd be a real squeeze. Let me just get 13 by itself. Okay, 13. Of the following choices, which type of collision is most likely to be the rate determining step in a proposed mechanism? And so remember, a mechanism has 2 or more elementary steps that are buried in this part of the reaction equation. They're inside here. You don't actually see them happen. You see the products and the reactants and products, but you don't see this. And we're inferring a mechanism, 2 or more steps. So which one out of all these choices, it will be the most likely to be rate determining? Think of it in terms of which one is most probable is not rate determining. Which one is least probable would be the slowest, the rate determining step. Which one of these collisions is least likely to occur as frequently as the others? I wish I had that. Is it what TV show is where they got the music in the back? Jeopardy. Yeah, Jeopardy. While you're thinking, the least likely one to occur is the one where you have to get the most number of reactants together at one time. Keep going. Which one has 3? Yeah, termolecular. The termolecular, you have to get 3 reactants together at just the right energy and just the right orientation. And the probability of that happening is very, very small. So it would be the slowest reaction, the reaction step, right? Termolecular. Non-molecular, I just made that one up. It doesn't mean anything. Okay, 14. Let's see. Yeah, we just need that much. Okay. For this reaction, 2H2O2, which is hydrogen peroxide, yields 2 waters and an oxygen. And we saw that reaction of the catalyzed version in that little video. Okay, where they poured the potassium iodide in there and it exploded. This is the reaction that occurred. Only this doesn't have a catalyst in it. It doesn't say it has a catalyst. So if we say it has the this mechanism, right? This 2-step mechanism. So the first step is H2O2 plus I minus yields H2O. plus IO minus. And then the second step is H2O plus IO minus yields H2O plus O2 plus IO minus. Let's see, is that a valid mechanism? Can we add these two together and get that one? Well, yeah, we got two of these here, right? Those are good. They're not canceled on the other side. We got two waters on this side. That's good. This iodine cancels that iodide. And this, whatever that is, IO minus cancels that IO minus. So yeah, it meets that condition. But which one is the catalyst? It's the one that goes in this side, comes out the other side, essentially unchanged. Okay. So there it is right there. This is the catalyst. Now, is this a heterogeneous or homogeneous? I didn't write the phases in there, right? So this is going to be in solution, aqueous solution, aqueous solution, all these in aqueous solution, except this one's going to come out as a gas. But the reactant and the catalyst are in the same phase. It's a homogeneous catalyst. Okay. Well, if that's the catalyst, what's this thing? See, let me draw a different shape around this. What's that? It's not part of the question, but since we got it up there, that's an intermediate.
I don't remember the name.
I'm sorry?
I couldn't remember the name, but
Yeah.
I knew it's what it was.
Yeah, that's an intermediate. It shows up in here somewhere, but disappears before you see it. Right? You don't see it here. This one you do see. If we were to write this out, well, usually when you have a catalyst, you don't write it as part of a reactant. You write it here. Okay, so that would be A. And when they conduct that reaction that you saw in the film, 3% hydrogen peroxide won't give you a very dramatic reaction. It's too dilute. So you have to get hold of higher concentration. 30% works really good. I haven't tried it. I've got a bottle of 12% coming for some other reason. I'm gonna try it with that one and see if it works. Let's see, we're gonna skip this. And this one, here we go. We need these right here. Okay, now we're gonna use the method of initial rates for this experiment. Instead of writing everything up there, the equation there is manganate ion plus. We did this. Did we do this one in class? We did this one in class, didn't we? It looks familiar. It has the oxalate plus the manganate plus hydrogen ions yields manganese 2 plus carbon dioxide plus water. Okay, what's the question? What's the order of the rate law with respect to MnO4? So we only have to do one determination, just to find the order of MnO4. All right, so which one of those? We use different values. I don't know. Let's take it as it is. So we have, see, maybe I can use my. There it is. Where did it go? There it is. Okay, so what do we need for initial rates to determine the order of MnO4? Well, we need to be able to write the rate law for each equation, for each experiment. These are 4 separate experiments. So if we go to this one, it changes from here to here. The other condition is we need the other factors in here to be unchanged. So that one doesn't change and that one doesn't change. So we can use the first one and the second one to set up our ratio. And that's what I'm going to do. So if we're looking for the rate law, right, we would write this K value MnO4, right? And H2C2O4. Yep. And then H plus 0. And this would have an N order, an M order, and a P order. But what we're going to do is we're going to take the rate for the second reaction and ratio it to the rate of the first reaction. Now, why did I do that? Because the second reaction has a higher rate. So if I put the rate of the second one on top and divide the smaller one into it, I'll get a whole number, or I'll get a non-fraction. Okay, so, and these are all going to be relative to their experiments. So when we write these, the rate of the second one is 8 times 10 to the minus 4. 8 times 10 to the minus 4, and that's molarity per second. And then we're going to ratio that to 2 times 10 to the minus 4. Molarity per second. Right. So is this a fast or a slow reaction? It's a slow reaction. Right. So it should lend itself easily to student lab because it doesn't happen very fast. The ones that happen just like that, it's really hard to get a handle on it. Right? Some of them happen so fast they have to use lasers to follow the reaction. Anyway, we got these two, and now we have the rate constant, which is the same for both of them. Right? That's a constant, it doesn't change. So what's the value for MnO4 experiment 2? 2 times 10 minus 3, right? And for the first one is 1 times 10 minus 3. 3. And this is to the n power and the n power. And then we have these other two. Right? This one's 1, that was 1 for the hydrogen ions. And this is 1 times 10 to the minus 3 and 1 times 10 to the minus 3. And this one's to the P, and this one's to the N. Okay. Since these are the same, then they cancel. Right? And we're left with this expression. The K's cancel also. So now we have this ratio is what? Well, it's 8 divided by 2, which is 4. Right? And that's equal to this ratio to the n power. Remember, if you have x to the, let's see, x to the n divided by y to the n is the same as x divided by y to the n. Okay. So that means 2 divided by 1 is 2 to the n power. So n has to be 2. Okay. Now this is an easy one. This is the kind of thing you see on a test. But for the lab, when you do this for your results for your lab, you may not get these nice whole numbers. Right? So if you get a ratio here that's equal to something here to the n power, and it's not an even multiple, then you have to know how to solve that equation for the n. And usually what we do is take the log of both sides. Right? Just take the log of this side, the log of this side, which is equal to n times the log of 2. So log of 4 equals n times the log of 2. Then you can solve for n because you take this log over here and divide the log of that into the log of this, and that gives you n. Okay, so that's how you solve one that's not pretty. Messy equations. Okay, so n equals 2 is C. C is the answer for this one. And if we wanted to know the others, we just go ahead and do the same thing, only we pick the experiments that allowed variation for the factor we're looking for, and the others remain constant. And that's determined when you design your experiments. Right? If we have 3 factors, the minimum number of experiments you need is 4. So if you have 5 minimum numbers, 6 experiments. All right. And this is 18. Let's see. Right, that diagram is for the following problem. So we'll stay right here on 18. All right, the rate law for this reaction is K equals, excuse me, rate equals K times NO to the second power and oxygen to the first power. That's a coincidence. Now, the coefficients for NO in that balanced equation is 2, and the coefficient for oxygen is 1. But that's purely coincidental. These values had to be determined experimentally. What happens to the rate when the concentration of O2 is tripled? Okay, so we've got the same kind of problem as we did before. If this one is going to be tripled, 3 times that concentration, what happens to the rate? Well, it's to the first power, so the rate should be tripled. Correct? Okay. If we triple this one, it would be 3 squared, it'd be 9 times. All right, that was 18. And oh, we're not going to do this one. Potential energy diagram. Maybe there's another one down the line. If there's not one down the line, then I'm going to come back to that one because you need to work with that diagram. 24. What fraction of a reactant remains after 5 half-lives of a first order reaction? So a first order reaction equals something here, say A, to the first order. So if it's a first order reaction, which half-life are we using? We're using the 0.0693 over K. 0.693. Okay, but do we really need that? It says, what fraction of a reaction remains after 5 half-lives? The first order reaction part here is superfluous because that doesn't tell us how much is left over. That just tells us what the half-life is equal to. And if we know K, we can calculate it. But if we're going through 4 half-lives, here's the easiest way to deal with this one. If you have your initial amount after 1 half-life, right? How much should you have left? Half of it, right? If you do another half-life, you should have what? A is 0, 2, half of that, right? So it's actually 4. Okay, do another half-life. It should be A0 over 8, right? Half again. So we do another half-life, that's 1, 2, 3, we need 2 more. So another half-life would be 16, and another half-life would be 32. So 1/32 of your original is what you will have after 5 half-lives, which is what? 2 to the 5th power. Let's see. 2, 4, 8, 16, 32. Yep. That would be the quick, easy way for math majors. But this is the way that explains it according to our chemistry. 24. Let's see. The following question refers to this reaction. Let's see, yeah, that's it. So let's just position that one. 2A2B2 2C. This is number 25. So we're referencing 2 diatomic A plus 1 diatomic B yields 2C. Okay. And we're given step 1 is a proposed mechanism. Elementary step 1 is A2 plus B2 yields C. Yep. Open R plus C. Got an intermediate. And then step 2 is another A2, right? Got another A2 over here, plus that intermediate yields another C. So we have 2 C's, we have 1 B, B2 here, 2 of those, 2 of those. So we're good. Okay, which step is the rate determining? Well, let's see. We're saying this one is fast, and this one is very slow. All right, so the rate determining step is the slowest one. Okay. It would be this one, step 2. C. If we had to write a rate law from the elementary steps, how would you do it? I'm not sure I should have one of those in here. We already got that one answered, so let me look and see if there is one. If there's not, I'm going to use this one right now. So let's do this. Oh yeah, there's, okay, we'll come back to that. Okay, so I'm going to go back to 25. Oh. Here we go. If we were going to write a rate law, where would we start? Remember, elementary steps, you can use coefficients. So we would write the rate law for this one, because that's the rate determining step. So we would say the rate is equal to K times first order A and first order R. Okay? That's a problem, right? Because there's no R up here. All right. This would be a problem unless we say if this one's a fast one, then it has to be a fast equilibrium, more than likely. What we would have to do is write the expression for this one and solve for R and plug it back into this one. Okay. If we did that, let's see. We wrote it for this one, that wouldn't work. We have to write it for that one. That means, okay, it won't work unless it's a fast equilibrium. We've got to be able to write this one in reverse. All right, so forget that. We don't have the proper conditions here to do it. Moving on. Let's see here. All right, this one stands alone. 26. How we doing on time? Okay, we're good. For a reaction where this one yields products, A0 is 6.4 molar, and the first 2 half-lives are 60 and 30 minutes, respectively. If this reaction is known to be zero order, calculate K. All right, so let's draw a little table. A here and time here. At time 0, A0, the starting amount is 6.4 molar. Right? The first half-life is 30 minutes. Right? 30 minutes is the first half-life. So we're at 30 minutes. and we have 3.2 molar. Second half-life is, oops, sorry. First is 60. You guys are gonna let me get away with that, aren't you? And 30 is the second half-life, which would be 90, correct? And the half of that would be 1.6. Right, half of that. Okay. If the reaction is known to be zero order, what's the K? Okay, so zero order means that the rate equals K. Right? Because if we put this one in here, right, that just drops out. So the rate is equal to K. So half-life equals A 0 over 2K. Yeah, we can solve that. Right? Just which one are we going to pick? Well, if we pick this one, we're told that it's zero order, so we don't have to finagle it. We don't have to try both of them to be sure of what order it is. Right? So we could use 6.4 here and 2 times K, and then that would be equal to the half-life of 60 minutes. Okay. So what would that be? Well, let's see. We're going to bring K over here and 60 over there. Right? Bring K over here and 6.4 over 2 times 60. Okay. This just swaps place with K. So 6.4 divided by 120 is what? 5.3, two significant figures. 5.3 times 10 to the minus 2. Okay. C. Okay. I'm starting to make it more complicated than it needs to be. You should be able to do the same thing with this one, only with A0 here. You would start with 3.2 and use 30 in it here. And you'd still get the same result. Okay. Now it's 26. Let's see. Looks like we got some repetition. We're going to skip down to 31. It's not going to move for me. The rate constants for a reaction at two different temperatures are given below. What's the activation energy for this reaction? All right. So at 30 degrees, see, 30 degrees, our K is equal to 1.38 times 10 to the minus 4. And at 49 degrees, K equals 1.21 times 10 to the minus 3. Okay. So we're looking for activation energy. We need, be sure it's here. Okay. There it is. If we were to plot it, we would plot it using this equation. Log K E or that's 1 over T plus log A, yeah, log A. And that way we could get the slope of the line here. But we've also got another equation. I don't know if I put that one in the lecture. Another equation that takes two different temperatures. But that's in here in your useful information, just under this equation. K2 over K1, this one equals just same thing here. And this one is 1 over T1 minus T2. Right. And the A's gone. Right. So for this one, we can just use the raw data. Well, with modification. Plus 273, plus 273. Because the temperature has to be in K. All right. So if we do that, we can fill in the values. This is going to be 2, the second one, and this is going to be the first one. Just so we keep them straight here. So the second one is going to be natural log of K2, 1.21 times 10 to the minus 3, and K1 is 1.38 times 10 to the minus 4. Then we have EA, that's what we're looking for, divided by what's R equal to. 8.3145, I think. No, 4. Yeah, 8.3145. That's joules per mole. Okay. In case you're interested. And this is times 1 over T1. This one. So that would be 303, wouldn't it? Minus T2. Let's see if I can do that in my head. 2, 2, 3. There we go. So now we can solve for this one. Right? Am I losing anybody? You're good? Okay. So I need 1.21 exponent minus 3, and then divide that by 1.38 exponent minus 3. And then take the natural log. There's my cube. So this side of the equation is 2.1711. And this side of the equation, let's do this one first. 303, take the inverse, and then 322, inverse, subtract that. So this is going to be 1.947 times 10 to the minus 4. And that's the same there. So we need to divide this one into that one. 8.3145 divided into that is, that's okay. This is E sub A times, this one divided into that one is 2.342 times 10 minus 5. And that's equal to this. So now to get E sub A, we just need to divide this one by that one. I'm just checking the calculator. They're already in there, so I can just hit the divide button. That's the way they are. Yeah. So E sub A equals 9.27 times 10 to the 4th joules. It's in kilojoules. So what's that in kilojoules? Well, it would be 9.27 times 10 to the 1st kilojoules, correct? Right, because we take 1,000 of these and put them into the unit. That's the kilo part. So 10 to the 3rd goes in here, leaves behind 10 to the 1st, That means 92.7 kilojoules, which is B. Okay. No questions? Just a yawn. Burning midnight oil. All right. So these equations so far that we've used are all in the useful information. You just have to be able to find them, know what you're looking for. Okay, how about this one? Let's see. There we go. 32. I need to switch. Consider the following balanced equation and the experimental results that follow. I'm going to write this just for clarity. 2 NOs, this is the gas, plus 2 H2s, this has to be gas. So I have to write it in. Yields into gas plus H2O gas. So either this is happening at low pressure or this is exothermic. That water would normally at room temperature be a liquid. Okay, so we've got an experiment here. What's the rate law order for NO and H2? Okay, so we have data. I'm going to put the data underneath here. The rate, I'm going to put the rate over here. Right. So the rate for the first one is 0.6, 1.2, and 2.4. And then the values, concentrations. These are 3 separate experiments, aren't they? With 2 reactants. Okay, so this one is 0.15, 0.40, and 0.20. This one is 0.60, 1.2, and 2.4. These are molar. Okay. What's the rate law orders for? So we just need to know the orders for NO and H2. All right. So if we want to get at what's the overall, let's write the overall rate law anyway. Right? It's going to be some K times NO to the N to that N, and then H2 to the M. Okay, so if we ratio, right, just like this initial rates before, if we ratio to get this one has to be the same, but it's not. Right, so we can't use initial rates. Anyway. Oh, I wrote it wrong. I'm sorry. You're going to let me get away with this. You know why I wrote it wrong? Because I put the rate on this side. And I was reading the wrong column. All right, let's try this again. 0.15, 0.30. Now for this one is 0.02, 0.04, and 0.02. Now, here we go. Now I can carry on with my argument. So, if this one's going to change, right, from here to here, then that's good. This one is constant from here to here. Right. So for the first one, we have, we're going to put this one on top. Let's see, this is first second, and third experiments. So we're going to put third over first to find NO. Right, so the rate for the third one is 2.40, and for the first one is 0.60. Right? So the expression for, and if we're going to hold H2 constant and K cancels out, all we need to write in is what is the NO. Correct? Okay. So this one is 0.3 and 0.15. 0.3, 0.15. So this one is going to be, what is that? 2? 2 to the n is equal to, what's this one? 4? 4 times 0.6 is 2.4? Yeah. So n equals 2, correct? So this one is 2. So let's do the same thing for hold this one constant, and this one changes. All right, so this one's going to be second and first. All right, so the second one is 1.2 and 0.6, and that's equal to 0.04 to the m and 0.02 to the n, correct? Yeah. Okay, so this one is 2, and this side is 2 to the n. So in this case, m equals 1. Okay. So the answer is C, 2 and 1. Pause for reaction. Everybody okay? All right. All right, that's 32. 33. We'll just, let's see, can we get, nope, I have to stick with 33 right here. The first order decomposition of H2O2 at minus 28 occurs with a half-life of 50 seconds. Okay. All right, so the temperature, let's put this stuff up here, minus 28 degrees C. And we're decomposing H2O2. Right, we know what the products are, but we're not going to need them. Half-life of 50 seconds. So if we've got time here and concentration here, then at 0 time, we have something, and we're given the concentration is 25.2. Right? And the first half-life is 50 seconds. Okay, so that means this would be what? Let's see, 2, that's 1, 2, 7, and 6, right? 17.6 would be for the first half-life. What would be the residual concentration after 5 minutes? Okay, we're also told what? First order. So this is a first order reaction. That means the rate is equal to K H2O2, just like that. Well, we got half-lives here. We need something that we can work with, right? So first order half-life is, remember, it's the one with no A value, just that one. Check this out. Yeah. All right, so we can figure out what K is. Right. We know the half-life is 50 seconds. 0.693 over K So K is equal to 6.693 divided by 50. And K is 1.386 times 10 to the minus 2. Okay. Now we know what K is, but this doesn't introduce a time factor in. Right? That's the differential rate law. We need the integrated rate law for the first order. First order integrated rate law has natural log, right? Yeah, natural log minus KT. So the first order is A equals minus KT plus C minus. I think that's right. Yep. Now we got something with time in it because we want to know what the residual concentration, what's left over, what is the actual concentration at 5 minutes. Now we've got K. We've got an initial concentration. We've got a time of 5 minutes, but our K is in seconds. So we need, what's seconds out of 5 minutes? Too much for you? 300, right. So time is equal to 300 seconds. And we know K. So this value is equal to minus the K value here, 1.386 times 10 to the minus 2 times time plus the natural log of 25.2. There we go. So, oh, I forgot to put time in here. It's 300. There we go. Now we can calculate that whole right-hand side because they're just numbers. I'm going to start with the log of 25.2, the natural log. Okay, that's 3.2268. And then I'm going to say 300 times 1.386 exponent minus 2 times that. And that's a negative, so a negative and a positive. So that's negative 9.3116 times 10 to the minus 1 equals the natural log of A. So we need to take the anti-log of this value. Right? And on your calculator, where's the anti-log? It's the base to that power. Right, so it'd be E to this power. It's already in here, so I just need to find E to the, here it is, where's my key? E to the X. And that means that A concentration after 300 seconds or 5 minutes is equal to 0.3944 C. Okay. All right. We didn't even need enough temperature, did we? That was just blue smoke, but not from Canada. You see the blood red sun this morning? I didn't get up that early. Just over the trees. It was just as red as it could be. It's all the smoke in the air.
Yeah, from Canada.
Mhm.
You see what New York looks like right now?
It looks like Los Angeles on a summer day.
They said that
Smog.
Is it says has the most smog in the world right now.
Mm-hmm. Yeah. Thank you to the to America's hat.
They were.
The reason they're having those wildfires is poor management, land management.
New York now has the worst air quality of any city on earth. That's what they're saying.
Yeah. Okay, so 34. Good on time. We got 1 hour left. For the second order reaction, NO plus O3. O3 gas. What's O3? Remember? NO2. That's ozone. Ozone. Ozone is supposed to be in the upper atmosphere. Or maybe if you get an even pure air purifier, it produces ozone. Because it does two things. It kills bacteria pretty efficiently. And it also ionizes dust particles and make them stick together when they drop out of the air. But it used to be ozone was produced in significant quantities from laser printers. The earliest laser printers were notorious for ozone. So their first solution to the problem, if you found a really, really old laser printer, like those old Hewlett-Packard laser jets, big guys like this, and open them up, you'll find a pack of activated charcoal in them. That's what they use to absorb the ozone. But then the technology improved and they don't produce any ozone significant amounts now, so they don't have to do that anymore. Okay, this is a second order equation. Right? Let's read the question. What's the rate constant at 233 K? The rate law, we may or may not need this, but the rate law is going to be NO to the N O3 M. There's your constant. What are we given? The rate constant has been measured. 1 times 10, 1.08 times 10 to the 7th at 298. So let's see, this K at 298 K equals 1.08 times 10 to the minus 7. No, 10 to the 7. Okay. And the activation energy has been measured to be 11.4 kilojoules per mole. So E sub A equals 11.4 kilojoules per mole over the temperature range 195 to 304. So it brackets this right here, 195 to 304. And so it brackets this one right here. That's good. You need to know that. What's the rate constant at 233? And so we want to know K at 233 K. Let's see, let's make that a little K like this. That's the question. All right. Which equation are we going to use? We're going to use the one we used before. Right, natural log of K2 over K1. Okay, equals E sub A over R times 1 over T1 minus 1 over T2, I believe. Yeah, 1 over 2. Okay. So let's see. We have E sub A, right? But this is going to be, see, since R is in joules per mole K, we have to convert E sub A into joule. And so how do you do that? Well, I take the K and say, what is K equal to? It's 10 to the third. Right? So then we have 1.14 times 10 to the fourth joules. And that goes right here. There, this is 8.3145. Right. Now we have temperature 1 is this one, right? As long as we keep them, this one associated with that one, it doesn't matter which one we pick. But if I pick this one as T1, then 298, and then T2 is 233. Right? That means that the K here, K1 is associated with 298. Right, 1.08. This is where you can get mixed up. And then K2 is our unknown. Okay? So we can do the right-hand side. It's all numbers. So let's take the inverse of 298. And then the inverse of 233. Subtract. So it's minus 9.36 times 10 minus 4. And I'm going to multiply that times 1.14, 8.4, and then divide it by 8.3145. So on this side, we have minus 1.2835. And on this side, now how do we deal with a log like this? Remember your rules for logarithms? The log of A divided by B is the same as log of A minus the log of B. So we're going to have the log of K2 minus the log of 1.08 times 10 to the 7. Now we can take the log of this, since it's negative. Let's see what it is first. Let's do that. 1.08 exponent 7. Take the natural log. And this value right here is 1.6195 times 10 to the first. So that's a negative on this side. It'll be a positive on that side. So we'll add it to this one. So now we have 1. Let's just do it this way. Standard notation, 14.912 is equal to the log of K. So now we just need to do the anti-log of this value. So e to the x. And K2 is equal to 2.9, two significant figures. 99 times 10 to the 6. C is the closest one. Rounding errors. Okay. If there are logs involved, the rounding errors get really amplified. So in this case, since you have answers for every one of them, pick the best one. If you had, say, E was none of the above, and yours didn't come out exactly like that, then you could argue that your answer is correct if you say none of the above. But you'd have to prove it. Show me your work. Now it's 34. All right. And who's next? Got to be getting a graph in here pretty soon. Interpret a graph. There it is. Okay. 39, 40, 41 are referencing this graph right here. Okay. Too bad I can't split screen. Let's see. 39, 40, and 41. Okay. So we've got energy on this scale. And we've got progress of the reaction on this one. And it looks like it goes from way up here for the reactants to way down here for the products. And then one of the traces goes like that here. And the other trace goes like that. Okay. So between here and here is A. And B is between here and here. And C is between here and here. Okay. And E is between here and there. Okay. And F is between here and here. I get everybody? A, B, C, D. D is between here. Here's D. Okay. Now let's look at the questions. So I've got the drawing up there. Use the potential energy diagram to answer the next three questions. Which letter shows the activation energy without the catalyst? Where's the activation energy? Between here, reactants, and the activated complex. So without the catalyst, it's between here and here. So E is without the catalyst. If we have a catalyst, then you need the other trace. This one, it's lower activation energy. That's A. Okay. And 41, activation energy for the reverse reaction without a catalyst. So in this case, we're saying we've got to go from here, put enough energy in to get to there without a catalyst. So we're going from here to here. C. Okay. That's how you read that graph. Let's see. Oh, scooch this over a little bit. There we go. Okay. And instead of drawing this one on the board, let's see. We're going to answer following two questions. Okay. Okay. All right. I'm gonna have to scroll back to it, but
What was 40 and 41? Sorry.
40 is A and 41 is C. Instead of trying to draw the next graph up there, I'm going to put the questions up and then we're going to go back to the graph. So 42 is asking what order is the reaction with respect to SO2 CO2? So the order for this one, SO2 CO2 is 2 to this value. We're looking for M. 43, what's the value of the rate constant? So in this one, K equals something. Okay, so let's go back to the graph. So you can see, yeah. So notice we have a straight line, right? And what are the coordinates? Well, let's see, I kind of messed up the coordinates a little bit. Time on the x-axis in seconds. And natural log on the y-axis. So if we're plotting time against natural log, which order is that? Zero order would be the raw data. First order is the natural log. So this is a first order reaction. N equals 1. Okay. So that should be B. Yeah, M equals 1. Okay. Now, if that's a first order reaction, and the equation is y equals minus 2.20 times 10 to the minus fifth x minus 8.87 times 10 minus 5. Let's go back to now that we know it's first order, then we're plotting, the equation is actually log of something. And this is minus KT. And this is minus log. Let's see. Actually, it's plus log. Plus log of A0. Okay. Yeah. Okay, so that's how you interpret that, the straight line formula. This is the actual log of y anytime t, but we're looking for k. Right? So k, if this is t, then this is negative 2.20 times 10 to the minus fifth is negative k. So there's your k, right? Okay, let's go down here and be sure it's selected right. Yep. K is B, 2.20 times 10 to the minus 5. We drop the negative because of the way the formula is written. It's negative K times T. So K is actually just this part of the number. All right, that's how you interpret that graph. Right. So who's next? Oh, is that it? That's it.